Let's now switch gears and start working with Google's library for numerical computation, TensorFlow. This library can do most of the things we've done so far. However, it has a very different approach for doing so. And it can do a lot more. And we'll get into that. The major difference to take away from the remainder of this session is that instead of computing things immediately, we first define everything that we want to compute, and then we'll later compute it. We define everything in what's called a graph. So everything in TensorFlow takes place in a computational graph, and running and evaluating anything in that graph requires a session. Let's take a look at how both of these work, and then we'll get into the benefits of why this is useful. All right, so I'm just gonna clear my screen, and then I'm going to import the TensorFlow library. Let's take a look at how we might create a range of numbers. So using NumPy, we could, for instance, use the linear space function. Immediately, the result is given to us, an array of 100 numbers equally spaced from -3 to 3. We know from NumPy arrays that they have a shape, in this case, a one-dimensional array of 100 values. And a D-type, in this case, float64 or 64-bit floating point values. In TensorFlow, we can do the same thing using their own linear space function. But instead of an array, we're returned a TF tensor, and the name is linspace:0. Whenever we see this :0, that just means the output of. So the name of this tensor is saying the output of linspace. Think of TF tensors the same way that you would the NumPy array. It's described by its shape, in this case, only one dimension of 100 values, and it has a D-type, in this case, a float32. But unlike the NumPy array, there are no values printed here. And that's because it actually hasn't computed its values yet. Instead, it just refers to the output of what's called a TF operation, which has already been added to TensorFlow's default computational graph. The result of that operation is the tensor that were returned. Let's try and inspect the underlying graph. We can request the default graph where all of our operations have been added. From this graph, we can get a list of all the operations that have been added and print out their names. To do that, we'll use list comprehension. So TensorFlow has named each of our operations to generally reflect what they're doing. There are a few parameters that are all prefixed by linspace, and then the last one, which is the operation which takes all of these parameters and creates an output for the linspace. We can request the output of any operation, which is a tensor, by asking the graph for the tensor's name. What I've done is ask for the TF tensor that comes from the operation linspace. So remember, the result of a TF operation is a TF tensor. And remember that the same name that we had for the tensor x before was linspace:0, the same name that I've asked for here. In order to actually compute anything in TensorFlow, we need to create a TF session. The session is responsible for evaluating the TF graph. Let's see how this works. Now we can tell our session to compute anything we've created in the TensorFlow graph. Alternatively, we could tell the previous tensor to evaluate itself using the session. And then we can close the session like so. We could also explicitly tell the session which graph we want to manage. By default, it grabs a default graph. But we could have created a new graph like so. And then created a new session to use this new graph. To simplify things, we'll be working in IPython's interactive console. So we can actually create what's called an interactive session. And that'll just make things easier so we don't have to actually pass around the session object or evaluate things by explicitly defining what the session is. Now when I try to evaluate x, I don't have to actually explicitly define the session. We'll leave this session open for the rest of the lecture. So some useful differences between NumPy and TensorFlow, for instance, the shape. Normally in a NumPy array, you would just call .shape, but in TensorFlow, we'll actually have to compute those shapes. And we'll use the getShape method to do that. Or in a more friendly format, we can request it as a list. All right, now we're going to try and create a set of operations. We'll try and create a Gaussian curve. This should resemble a normalized histogram, where most of the data is centered around the mean of 0. It's also sometimes referred to by the bell curve or normal curve. So I'll create the Gaussian with a mean of 0 and a standard deviation of 1. Now I'm going to type out the formula for the Gaussian, and don't worry about trying to learn or remember this formula. I always have to look it up in textbooks or online. Just like before, amazingly, we haven't actually computed anything. We've just added a bunch of operations to TensorFlow's graph. Whenever we want the value or output of this operation, we'll have to explicitly ask for the part of the graph we're interested in before we can see its result. Since we've created an interactive session, we should just be able to say the name of the tensor that we're interested in and call the eval function. Let's try creating a two-dimensional Gaussian. And this can be done by multiplying a vector by its transpose. If you aren't familiar with matrix math, I'll review a few important concepts. And this is about 98% of the math that we'll need from neural networks. So please stick with me through this, and it'll be smooth sailing after this. First, to multiply two matrices, their inner dimensions must agree, and the resulting matrix will have the shape of the outer dimensions. So let's say we have two matrices. In order for us to multiply them, x's columns must match y's rows. I try to remember it like so. The inner dimensions of these matrices must match. The resulting matrix multiplication will have the dimensions of m by p. So in this case, x has m rows with n columns, and y has n rows with p columns. So I tried to remember it like so. If I have two matrices, x and y, and x has m rows and n columns, and y has n rows and p columns, in order for me to matrix multiply, their inner dimensions must agree, which means that n must equal n, and the result of that matrix multiplication will be the outer dimensions, so m by p. But our matrix is actually a vector, or a one-dimensional matrix. So we actually have a matrix of m by 1 rows, or a one-dimensional matrix. That means its dimensions are n by 1. In order to multiply them, we'd need this dimension to equal 1, and the resulting matrix to be n by n. Let's see how we can do this. Let's store the number of values in our Gaussian curve. And then we'll multiply the two to get a 2D Gaussian like so. In order to get the result, I'll execute the graph. And I'll feed it directly to the imShow function to show it as an image. So what we've just done is take our Gaussian in one dimension, which looks like this, and multiply it by another Gaussian, which looks like this. So the resulting Gaussian, when multiplied, looks like that. So what we've just done is take our one-dimensional vector, make it a row vector, and then multiply it by a column vector. The resulting matrix has a 2D shape of n by n.